everyone, and welcome to Teaching Physical Sciences. Today I am very excited about the show. I really am. Welcome, Tara. You're joining us for grade 10.
Thank you, Helen.
Yes, and we've got Dylan behind the buttons and Lindsay assisting him. Welcome to the two of you as well. Okay, so today we are talking about magnetism and electrostatics.
Correct.
Yes, and so there's been a lot of back and forth between the two. Oh, before I get into this discussion, you see, I'm so excited about this show. I really am very excited. But before we get into all of the bits and pieces, if you would like to join the conversation, which we would really like you to do, please remember to tweet us at VT Science. That's the letters VT and then Science, remember I before E, except after C. And Dylan will be watching the Twitter feed, so he'll let us know if you have anything to say. Okay, so magnetism and electrostatics. Now, everyone by now knows I'm a maths teacher.
Right.
So I have to learn bits and pieces as I go along, and it's really interesting. Science has always been interesting. Who wouldn't find it interesting, except for maybe a 15-year-old at times.
Except when you blow stuff up, then it's cool.
Yes, it is, actually.
The rest of the time, maybe not so cool.
No one has those kinds of stories from a maths classroom.
No, unfortunately not.
Okay, so when I approached you about the magnetism and electrostatics show, at that point I wasn't quite sure if they were the same topic or different topics.
Yeah.
And then we had a conversation and we decided we would talk about magnetism separately and electrostatics separately, and then looked at the notes and all sorts of things like that. And then, Dylan, will you pull up the 5-point teaching strategy, please? Okay, so, and I must just warn everyone that I haven't told Tara what I'm about to do, but Tara, I put your two 5-point teaching strategies next to each other. And I noticed that point 1 is different for both of them.
Yeah.
You've got used bar magnets and iron filings. Everyone knows that experiment, even us maths teachers.
But we're going to do it again because it's cool anyway.
Yes, it is.
Yeah.
And then in electrostatics, you say do a practical using balloons and pieces of paper. And of course, even maths teachers know that.
About that, yeah.
But from that point, it's pretty much the same 5-point teaching strategy.
Yeah.
We're looking at revise the concepts of an atom, introduce new content, redo the practical, which is whichever practical was appropriate, and then ask the learner. I really liked point 5. Ask the learners what they would include if they were teaching this section. Okay, Tara, I know you are itching to jump in, but I'm not finished my speech.
No, it's all good.
So this is really exciting for me.
Yeah.
Because then I went to the 3 pressure point slides, and let's compare those as well. So magnetism says the existence of a field is not only understood properly. The existence of a field is not understood properly in magnetism. Go to electrostatics. Exactly
the same problem.
Pretty much, yes, except replace magnetism with electrostatics.
Correct.
Yes. Point 2, field is a force and the effect of a force. And point 3, the link between the structure of the atom and behavior of an atom in terms of a magnetic field is not clear. I hope I read that correctly. Yeah. Okay, so Tara, where I'm going with this is, why are they taught in 2 separate sections?
Because they have 2 different endpoints, essentially. But somewhere in the middle they do link up.
Okay.
So you have your basics of magnetism, what is a magnet, and we all know about fridge magnets and those sort of things. And then electrostatics, we know about balloons. So you can all pull your jersey over your head and you can get your hair standing up, or you can shuffle your feet along the carpet and shock your mom. Those are your basics of your electricity. But somewhere in the middle, the 2 fields meet and you can actually make electricity.
Okay. So you haven't convinced me yet.
Okay.
Yes.
What sort of convincing do you need?
Well, if the teaching structure is so similar and they do meet, then why don't we just introduce the concept of fields and then just do a whole lot of experiments with magnetism and electrostatics?
Because a lot of the time it is a matter of opinion. So from my experience and from what I understand and how I've taught and the kids that I've dealt with over the years, I've found the problems in both sections to be the same or very similar.
Okay.
So when you break it down and you have a look at what the basic is, where does the magnetism come from? Where does the electrostatic field come from? They go back to the atom. And when you start teaching from that point, you then see what the similarities are. So they fall under different sections because they are slightly different in their end point, but where they begin or where they originate is the same point. They start in the atom and they move out from there. So I've taught them, and I continue to teach them from that point, because they originate in the same place. They might have slightly different endings, because they originate in the same place and the problems can be the same. I tend to put them together.
So now I'm going to see if I understand you correctly. So we've got the two sections. We've got magnetism over here and electrostatics over there.
Correct.
Both of them started over here.
Yes.
And when we teach them, we start teaching them from their endpoints and we teach backwards to their starting points over there.
You can. It does. Again, it depends on who you are as a person and how you understand it. I prefer to start at the atom and then move out. But what I do is I take a physical example. So you'll see on some of the slides that we've put together, you take your physical example, something that the boys and girls know, and they know that the thing that sticks onto the fridge is a magnet, and they know that when they rub their balloon against the hair, or in winter when they pull their dress off, they know that's called static, but they're not too sure what it means from there. And in grade 10, they've just come from teaching the atom.
Yes.
And the atom and what's part of the atom leads us onto how we get a magnet, and it leads us onto how we get charges in electrostatics.
When did they do the atom?
Now, at the end of the first term. They should have done the basics of the atom at the end of the first term.
Okay, and then it's physical and chemical change.
Physical and chemical change.
And then this.
Yeah.
Okay. Okay, so they've had a break from the atom.
Yes, so there's got to be a little bit of revision of the atom.
Well, that's nice. I always like revision.
Yeah.
And then you, as Tara, stands in front of the class and you say what to introduce?
I will. Okay, so if I'm starting with electromagnetism, I like to do a prac. So I'll show you. I think most people have done this. Most people love doing it because if you can play with magnets and you can play with unfilings and you can make pretty patterns, it's the coolest thing. Hopefully
okay, so just explain what you have underneath.
So what I've got underneath is a bar magnet.
Okay.
And you get different types of bar magnets. So that's a fattish one. I was looking for the wider ones, but we don't have the wider ones that actually work nicely anymore. They've been dropped too many times, so they lose their magnetism when you drop a magnet.
Okay.
And then I've got a narrow one. So I'm going to start with the blue and the orange one, because someone has very kindly, by giving it two different colors, they've told us one is north, one side is north, one side is south.
Okay.
Okay, so take your paper, take your magnets, take iron filings, and you pour them gently. And
you do this before you revise the atom?
Yes, so what I would do is I like prac. So I'm the type of teacher that will like blow stuff up just because we can, and play with a Van de Graaff generator just because we can, and like build electric circuits. And so I like doing practicals.
How do you show this to a class of 40 plus?
That is difficult. So what I would do is I would break them into smaller groups.
Okay.
If I can't find many magnets, I would try and get as many magnets as I can.
So this is something they can safely do themselves?
This is something you can safely do yourself, easily. So let me just try this again, because it didn't quite get the effect that I wanted. I put too much on in that last bit. We'll try again. So just gently pour this over. And what you should see is you'll see the outline of the magnet. But the coolest thing is that you start to see like a circular pattern starting to build up around the outside. I don't know if you can see it yet.
Yeah, I can see some lines over there.
So
and coming out.
It probably doesn't come out so well on the screen, but if you've got kids in a group and they're huddled around a table, you can then show them. So we've got our little rectangular magnets, and what we've got there in circles are lines.
Okay.
So then my question would be, well, why the lines? Why aren't they just blobs? Why isn't it just solid? And then I'd ask for answers, and we'll get various answers. But I won't give them an answer yet. I like to keep them guessing.
Comes back to that inquiring mind that we keep hearing from all of our presenters.
That's it. Yes. And unfortunately, not all kids have it, because today all you do is on your phone. You don't have to have the smartest phone, but you can get on the internet and you can Google it. Doesn't matter who you are, where you are. So we're not good at keeping the mystery.
Yes.
So I try and say, well, just tell me what you think it is, and then we'll wait and see. So getting back to your question about if you've got 40 in a class.
Yes.
So if you can't get as many magnets, or let's say 10 magnets, you can have 4 in a group, then what you would do is you'd ask the guys, you've done your pattern, you then come and have a look, ask them to draw it. So just do a quick sketch, and it's quite simple.
Can I move this for you?
Let's just move it.
How expensive are iron filings? Can I go and
They're
sell
not
those?
expensive.
No.
No, you're not going to make millions out of them, I'm afraid.
Okay.
No, you won't, unfortunately not. But I would get them, please tell me this is a non-permanent board marker, otherwise I'm going to get myself in trouble with you. Get them to draw it.
Yes.
And then just get them to draw what they see. Sometimes they will draw this, where it comes in at the middle, because certain magnets... So it doesn't look like much, but part of an experiment is that they make note of their observation. Okay. There's no right or wrong. That's what they see, and that's what they record. So if you've got a big class and you've shown them the experiment, get them to just make a note of it. Just draw the pattern, and then from there, you can start your explanation.
And what is that when the atom comes in?
That's when I start with the atom.
Okay, and how?
I go back to the very basics of an atom. So I remind them, again, I like to, not talk and talk, but I like pictures.
Yes.
So I do this. So my little atom has got protons. And if I want to challenge the class, I can say to them, what is the positive molecule? And it's got neutrons, however we want to show them. And then
yes,
I've got my electrons in levels.
Yes.
So depending on the class, depending on how long it's been since we've spoken about the atom, either do a little bit of a reteach stage. You remember that this is found in levels, these are found in orbitals, those sort of things. It does depend on how much detail you want to go into. But this is what they should know by now. So like I said, depends on the class how much revision you need to do. So when I've drawn this, I will then say, out of these, I ask them a question, which particles, which elements is the wrong word, particles is probably the best word, would you think creates the magnetic field?
Okay.
So I will then ask them based on what they know about the atom. So in other words, they should know protons don't move. They should know that neutrons don't move, but that electrons can move.
So you're putting the ball in their court.
So I'm putting the ball in their court.
How often do they get the answer to that question?
If you've got a child who's understood this concept well, they should get it within sort of 5 or 6 guesses.
I suppose
Very
they've got
seldom do they get it the first.
chance of getting it right.
Very seldom do they get it the first time because they've learnt they're just one-dimensional. This is the acid. This is the atom. There's protons in the middle, neutrons in the middle, and electrons, and they're there for chemical reactions. That's the big thing. We only think of the atom in terms of chemistry. We don't think of it in terms of physics.
Yes.
And this section is physics.
Yes.
So now what they will say is okay, but if a magnet's permanent, your protons and your neutrons will be permanent. That's the most common answer I get. Because your protons and neutrons don't move.
Okay.
That's what they've been taught. Golden rule, they don't move, only your electrons will move.
Okay.
So a lot of the answers are, okay, your protons must make it magnetic, or your neutrons must make it magnetic.
Yes. I can see the logic they've used to do
Absolutely,
that.
and there's nothing wrong with that logic.
Except it's the wrong answer.
Except it's the wrong answer for this. So you take that logic then, and you say to them, okay, let's think about electrons. When electrons move, do all of the electrons move all of the time? Are they the ones that can move here, there? And from there, I then work out to what scientists tell us magnets are, or if we're talking electrostatics, what scientists tell us charged particles are, and then I keep bringing it back to that.
Okay. How long would this take you, roughly, in a class to get to this conclusion?
I'd say, depending on how the class reacts, you shouldn't take more than half an hour to get to this point. And then, for instance, with the magnets, talking about what they call magnetic domains, which is what makes a magnet what it is. It's a region within the atom where all the electrons align in the same direction. So a lot of textbooks, don't know if we can still see, a lot of textbooks represent it like that.
And these are arrows.
And the arrows are the electrons.
Yes.
And if they're all pointing in the same direction, then it's telling us that this is magnetized. So in other words, you'll have, let's say, a north pole here and a south pole there.
Okay. If the arrows are pointing up, they're pointing up to north.
Generally.
Okay.
Yeah. So again, it does depend on how the textbook represents it. There's no formal, this has to be north, this has to be south. What it does is it's just showing it's all aligned. It's more in alignment. It's all in the same direction. Because if it's a non-magnetic material, or non-magnetized, which is a very different thing, then what you do is you'll have your little domain and you'll have your electrons totally out of alignment.
Okay.
So that means that substance can be magnetic. We've got to do something to it to get them to all line up in the same direction again.
Okay. And how would a substance that can't be magnetic be represented?
Like
or
this.
Is that okay?
So this represents your non-magnetized substance,
okay,
and a substance that cannot be magnetized, because it doesn't matter what you do, you will not get those to align and line up and move or show the same direction or face in the same direction.
Okay.
But very, very, very seldom is there a question asked about a non-magnetic material diagram form. Doesn't mean that there isn't somebody out there who's prepared to really delve deeper into what the kids are thinking, but mostly this is for magnetic and non-magnetized. So it is magnetized or it's not.
Okay. Now you said a little earlier that you would do this experiment, you would get to that conclusion, and then you would draw it back to the atom, and you would do the same for electrostatics.
Correct.
So I come back again to why not introduce both at the same time?
Because your electrostatics will lead on to current electricity.
Yes.
Okay. And I come back to the fact that it does depend on opinion. So, for instance, the way that our curriculum is designed is they've got what they call a spiral effect. So you've got a little bit in grade 10, introduce it. Mm-hmm. And then it builds in grade 11, and then it builds in grade 12. And so it's supposed to build like that. Does
magnetism go in a different direction than to electrostatics?
No. Electrostatics becomes more involved with the actual sort of calculation of the field.
Okay. Strength
of the field. What will happen if you happen to have, let's just say we've got an electrostatic, if I draw this, you talk about capacitors in grade 11, so this could be a capacitor, for instance. You will have an electric field that occurs, and you might have, because somebody feels like it, put a charged particle into the middle of that. Let's say it's a positive particle.
Okay.
The children are then asked to calculate what force that particle experiences, what is the strength of the electric field, that sort of thing.
Okay.
So it becomes more, rather than application, it becomes more calculation, theoretical based. There are a few applications, but it more goes along the theory side.
Does magnetism then fall away?
No, magnetism doesn't. What it does then form part of is something called the motors and generators section.
Okay.
And we then talk about how electricity is produced.
Okay.
We talk about what generators are, what motors are. So that's when you get the boys in the class generally get excited because you talk to them about remote control cars. And they can tell you that there's this little thing inside the car that drives the wheels, and then they can tell you all about cars and a starter motor. So that's where your magnetism leads to.
Okay.
Your magnetism then leads to, we can use a magnetic field, combine it with a magnetic field generated by a current, and we can get movement,
Okay.
which is a motor, or the opposite, you can make something move. Let's say make a magnet move inside a current field, a magnetic field generated by current, and you can get something else to happen.
Okay.
So that works more towards your application. There's still calculations and answer this type of question and how can you improve it and how can you make it stronger or weaker, etc., but it goes more to the application than pure calculation.
Okay.
So unfortunately they remain so similar the whole way through, but the outworking is one goes more on a practical viewpoint, one goes more towards a theoretical viewpoint. And then your electrostatics is then, it's a separate section in that we're talking about, you can then talk about voltage, as in the effects of voltage and your lightning and that sort of thing. And everybody asks the question, well, why can't we store lightning?
Yes.
And so my answer is,
you try catch it.
You do it, and you'll be a multi-billionaire. Forget about a millionaire, because if we can store lightning, if we can capture and store lightning, then most of the world's energy crises are sorted out, because lightning's got thousands of millions of volts of energy. Yeah. So there's a challenge for anybody who wants to now catch lightning. That's their job.
Okay, so you've now satisfied my question.
Okay, I hope so.
Because I didn't actually have an answer.
Okay, fair enough. Okay.
So, as far as I can see, the answer to the question, the reason why we don't teach them together, even though they are taught next to each other.
They can be so similar, yeah.
Yes, is that the one turns into more practical, being the magnetism turns into more practical things, and the other one turns into theoretical calculations and things
and
like
if
that.
you want to go into a slightly deeper, if you speak to your physicists, the people who are way more qualified in this than I am, they will tell you that there will be, within the actual atom itself, there will be slightly more, the differences are far greater than what we cover at school.
Well, I'm sure they are.
So, but for our purposes at school, the outworkings and where they lead to in grade 11 and 12 are different.
Okay, so you have filled up half an hour of the magnetism section, which is 2 hours long.
Yes.
Tell me more about what you would do to create the inquiring mind within the section.
Well, another thing that you can do, and again, it does depend on what you what you have access to, but for instance, yeah, sure. If you want to talk to your kids about things in nature, so you want to talk about, with electrostatics, you'll talk about lightning. But when it comes to magnetism, you can ask them to look up the aurora borealis.
Yes.
For instance. You can ask them to look up the Bermuda Triangle. You can, and as I say, it doesn't matter what background your school is from, there's always access to information somewhere. You can go to a local library. If you're fortunate enough to have airtime, you can get onto your phone quickly and have a look, Google it. So if I ask them to look up something, majority will just give you an answer to what you looked up. But there will be one or two who are like, oh, that's interesting. And they will make a note of 3 or 4 questions that they want to ask you when they see you in class again, or even if if you are doing it in class.
Yes.
They will then say, what about? And as soon as they start asking questions, then their friends go, oh, isn't that? And I heard that. And so they generate the interest within themselves.
Yes.
But you as a teacher have to find that one question that will start the what about effect. And that's not always easy.
No, it isn't.
So I found the one that really is the most controversial, and I don't always know the answer to it because every time I look it up, I find a different answer, is the Bermuda Triangle.
And most South Africans don't actually know about it.
Most South Africans don't know what it is. They've never heard of it. Same thing with the aurora borealis, for instance. We, in the Southern Hemisphere, we don't get to see it, especially where we are in South Africa. But it's something that we can learn about in another part of the world in a totally different setting. It's not hot like it is here. It's ice. It's North Pole.
Yes.
Those sort of things. So it just, I like the fact that it's more than just South Africa. And so we then have to ask questions, and then you get the arguments. Bermuda Triangle's rubbish. I heard that it's true. I looked up this. So then I might never answer the question in class, and they might continue the arguments for days within themselves, but it's got them thinking.
Yes. Do you have any clips that you play to them or anything like that?
I don't, unfortunately. What I do tend to do is, because I'm fortunate enough to be at a school where the boys have got access to that sort of thing. So what I do is I ask them to find clips.
Okay.
And the thing with information is that it changes every year. So the clip that I played last year, so old school. Oh man, that's boring. I've got one that's better. So I'm fortunate enough that I can make it their job to find something and show it to me. But other than that, generally, Aurora Borealis, I've used to use one off the National Geographic website, but I actually went to look for it yesterday and I can't find it anymore. And I wasn't clever enough to download it in years gone by. But that's probably my favorite. Bermuda Triangle, okay, cool. Things disappear apparently, but for me it's the beautiful colors.
Yes.
And the way that light interacts with the magnetic field. That used to be my favorite clip. But as I say,
I'm sorry,
wasn't clever enough to download it.
Well, okay, so would you do any more practical experiments? I know you've got to talk about, and you've touched on Aurora
Borealis, that one.
Thank you.
Yeah.
And it says in the CAPS document that you've got to talk about true north and magnetic north, and I'm sure you'd bring that up at that point.
Once we've got them, I've sort of given them something to do, and it does again depend on how long it's taken me to do that theoretical explanation. Because one of the other things is once you've linked the atom to the domains or the areas of magnetism within an atom, you then have to explain how we make magnets and the different types of materials that you get. So there's only certain materials on the periodic table that can be magnetized or are magnetic. The most common one and the one that most people know is iron. And so the term ferromagnetic, I'm writing sideways here.
Yes,
sorry.
You are.
I'll change it. My boys are used to me. I write in all sorts of weird directions. Hopefully that's the right way around now. Ferromagnetic is just a terminology. It comes from the fact that ferrum was the Latin word for iron, and iron has to be magnetic. So any substance that is not pure iron but has the ability to be magnetized is known as a ferromagnetic material.
Okay.
So we'll then talk about compasses, for instance. So how did the sailors 500 years ago, they didn't have GPS. They couldn't just whip out their cell phone and phone somebody and say, am I in the right place? How did they get from place to place? They used the stars. What else did they use? And so I then introduce compasses. Mm. If you get lost, what can a compass do? What does it do? How does it work? So there's lots of different things that you can do. It does depend a little bit of PT for the teacher. You can do lots of research and find out a million different things for magnetism. But the most common ones, and the ones that the CAPS document requires, is true north as opposed to magnetic north, that sort of thing. Yeah.
It does seem to be quite practical and quite short.
Yeah, it is. It is. And then, like I say, the most important, one of the most important things is how a substance is magnetized. So you then will explain how when we had those domains that were all over the place, what do you do to get that aligned?
Okay.
So the most common one is that you take a substance that is already magnetized and you drag it along your substance that you want to magnetize. So I will then get the boys to, let's say I've got iron nails, and iron nails are easily accessible.
Yes.
And so we've got a magnet or two, so they will take their magnets, and if this is my iron nail, they have to choose a side and they have to literally drag the magnet along the nail like that. And they can do it as many times or as few times as they like. And then we try and pick up pins, or they try and pick up iron filings. And then they try it again and see if they're going to pick up iron filings, or so that they themselves can see. And then what I do is I have them drop the nail. Because one of the ways to disturb your domain is to literally knock those electrons out of their spot. So if you drop it, you will lose your magnetism. So if it's not a permanent magnet, so then there they go again. They have to try and magnetize their substance again. Sometimes they get it right, sometimes they don't. So then they come up with all sorts of ways to try and improve it. But again, it's something for them to think about. It's a challenge for them.
It's also getting them practically involved, and
Well,
that whole back to inquiring
There's
mind.
nothing worse than sitting there and having someone talk at you the whole time. And unfortunately, there are some sections in science where that does happen because it's very theoretical. But when you can get your hands on, absolutely.
And even better if they can do it themselves,
That's
I
it.
assume.
And like I say, sometimes it's not easy to get hold of things, but anything that is, like I said, like an iron nail, or you can get fridge magnets. They don't have to be very powerful magnets. They'll make a difference.
Mm. Okay, so we're about halfway through, so why don't we move on to electrostatics?
Okay.
Practical experiments practical ways to introduce it.
Well, I've like I mentioned on the notes, I said balloons because balloons are cool. Because for some reason, picking up or blowing up balloons and then popping them and scaring the daylights out of the teacher is fun for kids. So if you've got,
I'm not fond of balloons.
No, I'm not a fan either. But it's one way to get them involved is they're desperate to blow up the balloons. So I use balloons.
Yes.
But like I say, I couldn't find any. So what I did is I cheated a bit and I bought some of the equipment that we've got. But you get material.
Okay.
You get
Would
plastic.
you like to hold it up to
I'll
your
hold
camera?
it up to there. But I just want to show you've got, looks like a really bad seat cover
Yes.
from years gone by. And this is Perspex, nice plastic. Actually, sorry, this is just soft plastic. This is the Perspex. We've got a funny little Perspex rod. I've got a straight Perspex rod. You can get them to, so for instance, like I'm going to rub it on my sleeve. So you get them to rub it on their sleeve, and then they need to put it on their hair and see if their hair rises, or they're going to tear up pieces of paper, and they literally, they don't have to be very big at all. I'll show you. They just have to be microscopic. I don't know if it's going to work. It does work better in winter when the air is dry.
This is a point I wanted to bring up.
Yeah.
Because, of course, at this stage in Gauteng, it's perfect weather for static
It's great weather for
electricity,
static
but
electricity.
maybe not so much in KwaZulu-Natal.
Well, that's the thing. And unfortunately, it doesn't help us too much when we have a work schedule to follow and we all have to follow it at the same time. So if we had a little bit of freedom and you could decide depending on weather conditions, it would be great. So, for instance, I was doing something similar with my grade 9s earlier this year when we were having the floods, when it was just pouring every day, and we got no static. That people were rubbing their hands raw, and we got absolutely no static.
No.
So I don't know if this is going to work, but we'll try it. See if we can pick up some paper. So literally, just take two substances, and hopefully this camera up here will get it.
For the viewers, we do have a small pile of paper at the bottom.
We do, and hopefully,
and
we've got
Tara's managed to pick up. Almost pick up.
There
we've got one.
I don't know if you can see that. I've got one to attach by magic. No, actually it wasn't. It was by Electrostatics, I promise.
And
so that's what you get. So you get the children to just do a variety of things.
And would you experiment with different materials?
I would, definitely. Because that's, you see, the more opportunities you get them to try things, the more you're going to get their brain to go, what if, what about, can we do? And I find that when they're thinking like that, when a youngster's thinking like that, then they're open to possibilities. They're open to things, open to learning. So the more they try and do themselves, and sometimes we're not going to get an answer, and we're not always going to get an answer they're happy with. And they're not satisfied with it. But, so I mean, if you can't source it yourself, you can ask the kids to bring things. But I find the best one, because most school jerseys are made as this sort of nylon
material.
It's not the nicest feeling material, but it's perfect for electrostatics. Take a normal ruler. I didn't bring a normal ruler, but a normal 30 centimeter ruler on your school jersey. Hold your sleeve out, rub it along there, try and pick up your paper. It's great. It's so easy. So if you try your ruler, one of my guys tried his lunchbox. It didn't work so well, but he tried the lunchbox, and we've tried pencil boxes and anything. Try glass, try plastic.
With the type of material they're rubbed against as well?
So if you try all your materials against your sleeve, for instance, and then they try it against their blazer, and some of them rub it on their hair. And if someone's got so I try and find as many different types of cloth as well.
Do you try and get someone to do a dud activity or dud experiment that they won't work?
Yeah.
But get them to carry on trying and
yes. So out of these, there will be some that are harder to do. So in other words, they're more difficult. Just doesn't matter how hard you rub it. Eventually, you might get something, and others where a particular combination might not do anything. So I will do a little bit of research, or from years gone by, I would have made a note that, let's say, this type of cloth and this type of plastic might not get a reaction.
Okay.
So then I will still put one of those in there for them to try, because they've got to be able to tell me, like, for instance, there's a perfect example. So
the Perspex rod and
this particular Perspex rod and this particular cloth, and we're getting nothing. So not all friction and not all interactions are going to give us electrostatics. And that's an important part of this section, because
I would imagine
when you ask, if I say, most people start with, so what causes static electricity? And everyone goes, it's friction, ma'am, because things are rubbing against each other. And in grade 4 and 5 and 6, they've learnt about lightning.
Yes.
And lightning is the water molecules rubbing against the dirt. And so they know the concept of friction and the concept of things rubbing against each other. And so they just assume that that's blanket.
Okay.
So you put in a few duds.
Yes.
To show that actually not all substances will have the same effect. So you're not going to get static from everything.
And they would then write down their observations.
It depends on how formal you want to make the practical. But it's a good idea to have them, if you've got Perspex and you've got plain plastic and you've got, let's say, glass, and you can even have a piece of metal, a strip of metal. And then I don't have silk, unfortunately, but silk is quite a nice one. Silk, your normal sort of ordinary cloth, mutton cloth, cotton, you have the different types, wool. And then I get just to put a tick or a cross. Yes, something happened. No, something didn't happen.
Okay.
And then if something didn't happen, why didn't it happen? Just 2 or 3 sentences why you think it didn't happen. If it did happen, what do you think happened?
Now, what is the importance of terminology in that kind of observation?
In that sort of observation, terminology I don't think is vital, because you just want to know what they've seen. You just want them to get used to recording what they've seen. Because what often happens is they try to please the teacher, so they're trying to give the right answer, and they will use terminology or big words that's not necessarily what's actually happened. So for me, the practical aspect is all about write down what you saw.
Yes.
Even if in the end it turns out it shouldn't have been that, we can then say, well, why do you think that happened? There's another avenue for us to investigate. So it's all about writing down what was observed.
Okay.
And then we will talk about, should it have happened like that? Shouldn't it? Can we explain why it happened?
Okay. Now, we've spent a lot of time talking about rubbing things. How long should this experiment and this process of observation take in a classroom?
Not too long. Again, maximum, I'd say 15 to 20 minutes. Depends on how big the class is. Depends on
really
how many
the
items.
First half of the
first half
lesson.
of a lesson, that type of thing. It depends on how many items you want them to test. Depends on how well behaved they are as a class. Unfortunately, if you have your naughtier classes, they do tend to take a bit longer, but it shouldn't take you hours at all. It shouldn't take you, I would say, half an hour max.
And it's just establishing the basics of
that's all it is.
Electrostatics.
It's got them. They're not just like, something else we have to write down. It's like, I know this, and I've done this with a balloon, and my hair stands on end, and all that sort of thing. So they can then in their mind make a connection between what they're actually doing now in science and they've done something similar before that's had nothing to do with science.
Yes.
And so they can now bring in their knowledge, their previously acquired knowledge, into what we're going to do.
Okay. On the second point of your 5-point teaching strategy, it says bringing in the atom, if I remember correctly.
Yeah. So again, like I did with electromagnetism, if you're doing this section directly after magnetism, or you can do it before. It depends on you, but it's usually, I think, magnetism and then electrostatics. You will then say, okay, guys, you remember the atom and what's going to move, and what is particularly important now is the fact that the electrons are moving. We don't need the electrons to line up anywhere. We don't need them to show their...
It's making more sense why it's taught separately now. Okay,
so
magnetism's electrons are straight, and this one, they're all over the place.
Yes, and we need them to actually leave atoms in this case. So with magnetism, it's more within your atom, how are your electrons aligned? How are they lining up? Whereas with electrostatics, it's I'm taking an electron from atom A over here. I'm taking an electron from atom A and I'm putting it over there to atom B. Now, what is that going to do? What effect is that going to have? So you will now end up, let's say, with slightly more negative charge. That will be a slightly more positive charge. What does that mean? Why have they moved? How does that affect their behavior? That sort of thing.
Yeah. At this point, I want to ask you something else that's slightly related, but not really. In the previous school that I taught at, we had a fantastic maths department and a great science department, but the science teachers split it. So the one would teach chemistry and the other one would teach physics. And I found this is more and more common the more I speak to science teachers. How does a physics teacher then explain this without contradicting chemistry teachers?
Well, you shouldn't have to contradict it because they build on each other. So if we go back to your structure of your atom, they would have learned, like I said, and you would have revised when you did in the last section, you've got your protons in the middle and you've got your electrons. Depending on how each person draws it slightly differently, but you've got the same idea. Everything's going in levels. So in chemistry, they are taught, and we learn, that your electrons are used as a type of currency. They are what make bonds happen. Electrons
and all chemistry teachers will teach it that way.
So they won't necessarily use those words, but it has to do with filling or emptying what we call the energy levels, which are these rings around the nucleus. So your electrons have to move. They either will be added to this atom or they will be removed from that atom. And you have like a running total that happens. So in this case, let's just add in a few more of these. In this case, we're going to have 6 protons. I don't know if I'm still on the screen here.
Yes,
and we're going to have 1, 2, 3, 4 electrons. Okay. So if this was a neutral atom, your protons and your electrons should be equal.
Yes,
and that's what we've learned in chemistry. It's a neutral atom. When there is there's a discrepancy in the numbers, it has what we call a charge. Either a positive charge or a negative charge. Your positive charge means that you've got more positives than negatives, or your negative charge being the opposite, you've got more negatives than positives.
Yes.
So that idea of the charges is where we're going with electrostatics.
So it's basically just a physics teacher briefly touching on what the chemistry teacher should have done in detail.
Correct.
Okay.
Correct. So you will then have, if they're teaching, it depends on how it's structured. If they're going to teach concurrently, so physics is happening at the same time as chemistry is happening, that could be a little bit difficult.
Ooh.
But if you are one teacher that teaches this section and then another teacher teaches the next section and you follow on one from the other, that should be a little bit easier to
I'm wondering how you would do that with the new work program and the CAPS document,
Very clever timetabling.
Okay.
Very clever timetabling.
Okay, but let's get back to your 5 points. So you have now introduced this concept and they've got it a lot faster because you did it with magnetism.
So it's not the third time that they're hearing. Basically, they've done it in detail. In term 1, you've gone over it briefly with magnetism. Now you're touching on it again with electrostatics.
Okay.
And the main part of electrostatics is the interaction of the charges. So how does your proton interact with your electron? So the laws of opposites attract. How do your electrons interact with each other? How do two protons interact with each other? And here you can bring in magnetism.
Yes.
You can say that imagine or pretend that your two protons are like two north poles. They are two of the same.
Okay.
And your kids will know from playing with the magnets, because even if you didn't tell them to, they would have done it. They would have put the two positives or the two south poles together and they will push each other away, or they'll put the two north poles together and they'll push each other away.
Okay.
So they would know, they would have experienced the fact that these two are repelling each other. So you can then bring in a concept that you've established or re-established with them from magnetism into this section as well. But that is not because of a magnetic field. It's not because of a magnetic field, so it's a similarity.
Okay, so you're not saying that the proton is like it is
No.
north.
So I'm saying, what I will say to them is, do you remember how the North Pole reacted when another North Pole came near it? They pushed each other away.
Okay.
So the same thing will happen here. When the proton comes close to another proton, they will try and push each other away.
Do they ever confuse it and say that all protons are north?
Sometimes they do. Sometimes they do. But it's very seldom, because what we do is you don't linger on this for too long. What you will do is you will take it to a bigger or a sort of macroscopic level, and you will talk about a charged element. So it's a little particle.
You brought up something. I'm going to stop you there quickly. John has been with us twice, and he keeps talking about the Johnstons Triangle. So, and where you've got the microscopic, the macroscopic, and the symbolic.
Yeah.
So, drawing the positives and the protons and the electrons, that would be the
microscope.
Symbolic.
Well, yes.
Okay.
But you're talking at it will be at a microscopic level, because those are the smallest things that can attract or repel.
Okay. Then going to this would be the macroscopic.
Macroscopic,
a little bit of a bigger picture.
Yes.
Okay.
So now we're talking. If you have a Van de Graaff generator, for instance, or we're now talking the balloon and your jersey, or the plastic ruler and the pieces of paper. Why do those two attract? So you've got a whole object with a charge, as opposed to a single charge.
Okay, I'm with you.
With me?
Yes.
Okay. So let's say this is our little piece of paper, and it happens to be, in this case, because we haven't charged it, it should be a neutral charge. But if I bring my ruler close, and let's say I gave it a negative charge.
That's been from rubbing
rubbing against the material. Electrons have gone from the sleeve or the shirt or the cloth onto the ruler. And then again, just to reiterate, I would then say, remember, the electrons are in the levels around the nucleus. They're the only ones that can move.
Okay.
So by rubbing the two together, we're allowing the electrons to jump onto the ruler.
Okay.
And then, why does the ruler attract the pieces of paper? That doesn't have a charge.
Yes.
So then it's not an opportunity for them to think it through. This is negative, that doesn't have a charge. But we saw the paper attach itself to the ruler. And so then they can then answer a few questions, and you can then talk about repulsion on a greater level. What happens is all these electrons here become scary, makes them sound like humans, become scary to the electrons sitting on the paper. So the electrons on the paper move away from the top. They try and hide under the bottom of they try and hide around the back of their own atoms.
Okay.
And essentially what they do is they're exposing the poor little protons.
And that would be the reason why another piece of paper would be able to pick up one below it.
Correct.
Okay.
Yeah.
Okay, so that is point 3 now of your
Yes.
teaching strategy. Point 4 was point 3 was introduce a new content in terms of the atomic structure. So I've got my numbers wrong.
Yeah, which is what we did, talking about how it's the electrons that move. Yes.
So I'm excited now, because now we're at point 5, which is the one I was really looking forward to, because we keep, off the show, we keep talking to our guests about how great it is as a teacher to reflect on your teaching practice and how you should. But you are actually the first person to bring it up on show. So
Okay.
yes. Tell us about this, asking students, because most teachers would run away scaring. Screaming, not
look
scaring.
at it. It's sometimes it is a bit scary because if you say to them, okay, if you taught this, how would you teach it?
Yes.
But I do it more from the point of view of, I believe that if you can explain it to somebody else, then you know what you're doing. So I would then say to them, okay, so pretend you're going to teach your teddy bear at home, or your pot plant, or your granny, or the budgie, or whatever it is that you've got at home. What are you going to tell them? Out of all the stuff that I've told you this because you have to know it, and they tell us that we have to teach you that. But if you were just telling somebody else about this, just so they could know, what would you tell them?
Okay, so it's more about them reflecting on their own learning.
It's more about them reflecting on their own learning. But from that, I then pick up, I'm able to pick up what they weren't too sure about. And so if they leave something out, I'll say, well, why did you not talk about the atom? I'm not too sure about the atom. I don't really see how it
Did they write this down?
I get to write it down. And it's not long. It's 5 points.
And
maybe.
You don't mark it. You just read through it to give you a general idea.
If I want to, it's peer assessment. Like, give it to your buddy, see what he says, see if he agrees, if she disagrees, that sort of thing. But it's just more a case of, if you were going to do it, how would you do it?
Okay.
And then I get one or two of them to say, I would say, okay, well, what do you say? Why did you include that? Why did you not include that? So the first time you do it is a bit scary because they're like, oh, because we didn't understand anything. It's like, okay, so I've got to go back and try something new. But that's fine. But that's the only way you learn. If you're not prepared to hear that they're not sure, then you're never going to know.
And do you make notes for yourself? For
I
next year, I must remember.
Yes, I do. You have a look at the back of my classroom. I've just moved all my files into my classroom. It's carnage. Everyone's like, where do you... But that's the stuff those are the notes that you make for yourself as you go along. I must remember this. I must remember that.
Yes.
Because you do. In a year's time, you'll forget. I'll probably forget by next week.
So there's a lot to do as a teacher and a lot of different content. Yes.
And sometimes you don't always remember to do it. And sometimes you look at it and you think, don't know if I agree with that. And you might have to do it 2 or 3 times to go, actually, maybe I should change what I'm doing.
Yeah.
It comes with experience.
And it's a great thing.
It's a good thing.
Yes.
It's a tough thing, but it's a good thing.
Okay, before we move on to the next thing, we're going to look at some links of mindset resources that we have. If anyone is looking for extra content knowledge, the first are a series of 3 links. And interestingly enough, the lowest link, not the bottom link, well, I suppose it's the bottom link, is a link to a lesson that's on magnetism and electrostatics. Yes. And of course, you have the advert happening. It's quite cute. Okay. And you see electricity, is it the same thing? Electricity and electrostatics?
Electrostatic means to stand still. Electricity is the flow of current. So that's why they
So I got that
separate.
one wrong.
They flow into each other. They move into each other. You go from electrostatics usually onto current electricity.
I know the next section in CAPS is electric circuits. Yes.
Which is now the flow. So you take a standalone charge where you can move a certain number of electrons from point A to point B.
Okay.
And then with current electricity, they just all move around the circuit as many times as you can get them to go around.
Okay. So half right.
Half right.
Okay, thank you. Okay, and then the next set of links is a set of links for electrostatics. And one of them is the same. The other one is just purely on electrostatics. And of course, I will put these links up on the blog, which should be uploaded tomorrow morning. So everyone is welcome to come see it. I'll try and find some other links to interesting things.
Look, I've got 1 or 2 written down. I'll see if I can
send them on, please. Okay, and that brings us to our last section, which is one last thing. Okay, so Tara, this has passed quite quickly.
It has.
Let me tell you a little bit about one last thing, because you are first time here.
Mm-hmm.
Basically, I'm reading this book called Teach Like a Champion. And it's written by an American called, I keep saying I think he's American because his name sounds, but I'm pretty sure he is, called Doug Lemov. And he has written a book that has 49 actionable steps in it that you can do as a teacher. And they're relatively easy to put into play. And to be quite honest, most of us are doing it anyway.
Yeah.
They're just intuitive things. But it's nice to think about these things.
Mm.
So every week I read one and then I put it on. And this week it says format matters. And it says it's not just what students say that matters, but how they communicate it. To succeed, students must take their knowledge and express it in the language of opportunity. So that's very poetic. And when you read it in the book, it makes a lot more sense than what it actually makes over there. But basically, it's saying that don't let the students get away with a one-word answer.
Correct.
Make sure that they say things with the correct word order if you're doing a language subject, or even in science, if they're doing their observations, they must do everything in the correct format. This one I don't think is that controversial.
No, it's not. And I think it links into what else when I make them put down how or what they would teach. Because you can't just say atoms. Okay, well, what about the atoms? So it is one of those things where often tests are badly answered because what is thought is not what is put on paper. So that's definitely something that we need to encourage. That's perhaps there is more writing required, especially in a subject like science. It's not just calculations. Maybe we do need a written explanation every now and again to check that they understand what's going on.
And of course, I know as a teacher, when I hear more writing, I think, more marking. But it doesn't necessarily have to be marked by yourself.
No, it doesn't have to be. It can just be, in 3 sentences, explain what you understand. Give it to your buddy. Do they agree with it? Don't they agree with it? It's just allowing expression.
And I suppose by giving it to your buddy, you're encouraging growth between the two of them because it's critical feedback as well as thinking critically about what's written in
and
front
it goes
of you.
towards peer teaching and cooperative learning. So often your friends can explain it to you in languages you understand better than, say, someone like a teacher who's possibly much older or might even slightly older, doesn't matter. But you do speak a different language. As a teenager, you speak a very different language to an adult. You've got cool words and slang and phrases and all that sort of thing that might make more sense to you if it's brought across by a friend.
Yes.
Just can't use them in the formal test.
No
slang, no cool words, nothing like that.
Sorry, are you saying that they can use the slang when they write down those?
No, I'm saying often when you explain it to a friend or a peer, you will use language that is common to the two of you to get a basic understanding.
But when they write it down?
But when they have to write it down or when it's for a formal assessment, it can't be the common language that you've used for understanding. It's now got to be one step deeper. It's now got to be the correct terminology, the way that the science teacher wants it.
Yes.
Tara,
thank you for coming. I'm very sorry I threw you into the deep
end. No, it's fine. It was my own fault. I happen to teach in the same way. Thanks.
Yes. And with all my excitement, I forgot to let yourself introduce yourself.
I'm Tara.
Yes. But we do know that we only ask people who are well respected, and obviously you are in your field. So thank you for coming.
Thank you. I've enjoyed it. It's been interesting. It's been very different.
Yes. Oh, good.
Thank you.
And thank you to Dylan and Lindsay behind the buttons. And we'll see you again next week where we'll be discussing grade 11 physical sciences.
Cool.
Goodbye.
Bye.